Here are the learning goals from section 2.4, along with some recommended textbook problems. We've already talked about classifying points of discontinuity, about the laws of continuity, which are those theorems from the previous video, and about the substitution method. What remains is this learning goal about making a function continuous by choosing certain constants. Consider this piecewise defined function. Is there any choice of value for that constant a which makes this function continuous at 2 or at -2? Pause the video and think about your answer. The key observation here is that the denominator x squared minus 4 includes a factor of x plus 2, which we see in the numerator. Those factors cancel out except when they're equal to 0. So what do we expect the graph of this function to look like? Other than the value of f at x is plus or minus 2, the graph will look like this. At x equals -2, where those factors canceled out, we get a removable discontinuity, because the limits from the left and the right-hand side are going to both equal the limit of this thing. At x equals 2, we get an infinite discontinuity, which is not removable. Now the word removable here, for removable discontinuity, actually means yes. There is a way to assign a value here which makes the function continuous instead of discontinuous. The left and right hand limits are equal. In fact, here they both equal -1/4. So that's what the function value should be to make the function continuous here. The infinite discontinuity is not removable. You can't just assign a value there that will get rid of this vertical asymptote. So if we choose that a equals -1/4, we'll fill in this open circle here, and then we'll just add a point to the graph here along that vertical asymptote. Still a vertical asymptote, still not continuous. That's the best we can do for this kind of function. Notice that if the function had had a jump discontinuity, then with the left and right hand limits not equal, we wouldn't be able to assign a value to that point making it continuous, but we would be able to assign a value making it either left continuous or right continuous. Now let's look at a little bit trickier type of problem. Now we have a whole interval where we want to define the function, and we're not going to set it to be a constant, but to be a line. So you want to find values for a and b that make this function continuous everywhere. Pause the video and try to solve the problem. When we go through the solution now, we're not just going to focus on what the correct numbers are for a and b, but what a correct write-up of the solution would look like. The question doesn't just ask us to make the function continuous at -1 and at 2, but to make it continuous everywhere. So we start by addressing all those other points. Whenever x is not on the borderline between two formulas, then the laws of continuity tell us the function is continuous, regardless of a and b. A and b are just going to be some numbers, so on the second and third portions, the function is a polynomial, and in the first portion, it's a composition and a shift of some functions we know to be continuous. Now we can look at the other points. Let's look at 2 first. What we need for the function to be continuous at 2 is that the left and right limits equal the actual function value. Your answer should show that you know that, should show that you're thinking about what is the limit of f of x as x approaches 2 from the right. Well, we can show that that equals 4, which also happens to be the function value. That means what we need to do is make the left limit also equal 4. And the left limit of f is 2a plus b. So this gives us one equation now involving a and b. We'll get another equation by looking at the continuity of f at x equals -1. We know how to calculate the limit as x goes to -1 from the left. It equals 1. And so that's what we need the limit from the right to be equal to. This gives us a system of equations that allows us to calculate a and b. Probably you haven't solved the system of equations for a while. Pause the video and try to remember one way you could solve this system. As I alluded to before, there's more than one possible way to do this. My preferred solution would be to subtract these two equations. And when you do this, you get 4 minus 1 on the left, and you get 2a plus b minus a plus b, that's just a. So 3 equals a. And once you've solved for either of the two values, then you can use one of the equations to solve for the other. So ultimately, we found those two numbers, a and b, as the question asked us to do, but that's not all we did. We justified why those are the correct choices, and we addressed the continuity of the function at all the other points. In the next video set, you'll learn some strategies for calculating limits when the function in question is not continuous and the substitution method does not apply.